The second speaker is going to be Sungguen Ryu, and he's going to tell us about beating Carnot efficiencies. So please.
Yes, thank you very much. First, thank you for the invitation for this wonderful conference. And I'm postdoc in the eFISC in Spain. And this work is done with the researchers Rosa Lopez, Yoren Sierra, and David Sanchez. And also our work is now in the archive here. So within the few slides, I will tell you about our motivation and what is the main results, and then I will talk you for the details in time. So our question of interest is what is the bound for efficiency of general heat engines limited by the second law of thermodynamics. So yes, as the previous talk nicely introduced, the general heat engine is like this. So you have a working substance and the two thermal bath, hot and cold, and you extract the heat from the hot bath and dump some of it to the cold bath, and the different amounts is extracted to the external object by work. So in macro engines, it's well known that Clausius relation is well satisfied. The Clausius relation is that the entropy is identified by the sum of the heat extracted from both reservoirs divided by its own temperature. And the second law of thermodynamics dictates that it should be positive. And these two together tells you that efficiency cannot exceed the Carnot efficiency, this value. And this is universal value. It's only determined by the temperature of the hot and cold bath, independent to the details of the operation of the engines. And in micro engines, in contrast, it is well known that some non-equilibrium control is available. For example, the works by Koski and Pecola, they demonstrated the Maxwell-Demon impossible using the quantum dot. So basically, they demonstrated Dillard engine. And in this kind of situation where the non-equilibrium is strong, the efficiency can beyond the Carnot limits. And in this situation, is it important to identify what is the entropy production? And furthermore, it has been demonstrated that if you use the non-equilibrium bath rather than thermal bath, there are merits. For example, Rafael Sanchez and Whitney and the others showed that non-equilibrium bath can act as a demon, so extracting the work beyond the Carnot limits. And also Scully and others show that if the bath have a coherence, it can be used as a resource, again extracting the work beyond the Carnot limit. So our motivation is that what is the effect of the non-equilibrium bath when it's driven by the AC voltages? And I would say such study is desirable and timely because recently AC experiments have shown that they have a great ability for controlling and measurement the single electron excitations. So this is the Leviton setup, which is also introduced by the great talk of the Gwendolyn Pfaff yesterday. And it is, in briefly, it's made of the Fermi C, not in the nano device. And you apply the voltage pulse to one contact. But when you apply Lorentzian pulse, it's very specific, it's special. And then it excites only electron excitation on top of the Fermi C, not exciting any holes. So, and furthermore, these single electron excitations has been measured in experiments by using quantum tomography, also demonstrated by Bisognin and Pfaff in this article. And basically what they do is the same thing as the quantum optics. They do the Hongo-Mandel experiments by colliding the levitons and some reference states. And like this degree of great control has had implication in a lot of applications. For example, in the electron quantum optics. So they doing the optics experiments like Hongo-Mandel or Humphrey-Brown twist using electrons. And they have implications in the metrology, like defining ampere using fundamental quantum pump. And also they have implication in quantum information as they can excite flying qubits and encode the entanglement or the superposition of flying electrons. However, in these systems, heat and energy currents are only of recent interest, studied recently by Dashti, Spetoza, and Sassetti, and others. So in this talk, we will show that there exists a general kind of the AC-driven quantum device, which shows the efficiency beyond the Carnot limit. And this is thanks to two factors, the AC driving and the chirality. The first factor, AC driving, violates the Clausius relation by inducing strong non-equilibrium to the electrons. And the second factor, chirality, due to this, this AC field does not inject power into the electrons, which is usually a diminishing factor for the power output. And we will also show that the second law of the thermodynamics is not violated when adopting the Shannon entropy as entropy production rather than relying on the Clausius relation. So now I will further give you the details of our results. First, the setup. So our setup consists of the chiral conductors here and here, for example, which can be implemented by the edge states of the conformal sample. And these are thermocoupled to the localized energy level, which is can be, for example, quantum dots formed by two quantum point contacts. And due to the chirality, we can put 4 terminals, 4 contacts. And on the left side, the two reservoirs are hot reservoirs, and we assume that they have a common chemical potential μL and the common temperature theta L. And on the right side, they are cold reservoirs, and we assume that they have a common chemical potential μR and temperature theta R. And we only apply the time-dependent voltage to one of the contacts here, the left input contact. And specifically, we consider the Lorentzian pulses, which excite levitons that I mentioned before. And I would like to comment that in this work, we only consider the charge and heat currents, which goes into the hot reservoir as sum of the two reservoirs. So we don't resolve the currents in each reservoir, and also the currents into the cold reservoirs. And also we only consider time average currents, and we don't focus on time resolved currents, which may show further interesting stories. So let us start with the simple situation. So when there is no AC driving, then this is already well studied, that first you have a energy dependent transmission by this localized energy level. And this induces electron hole asymmetry. And due to that, thermoelectric current is generated when there is a temperature bias from the left to the right. And this thermoelectric current can generate power when they have a temperature bias. And the power output is determined by the voltage difference multiplied by the current, thermoelectric current. And then efficiency in this heat engine, steady state heat engine, is determined by the power output divided by the work extracted from the hot reservoir. Now, let's consider the case with the AC driving. Then I will show you the details furthermore, but in summary, they dynamically induce electron hole symmetry. Like recall the levitons that I told you, they only excite electrons, not the holes. And due to that, the thermoelectric current is enhanced. But now we have to consider that there is another power associated to the AC field. So the AC field can inject power P in to electrons, which is working substance in our case. So this input power diminishes the output power. So the efficiency with the AC driving should be determined by the output power, which is competition of the power generated by thermoelectric current and the input power. So in this slide, I will briefly tell you the method that I used. So basically, we used Fourier scattering matrix formalism to determine the currents and power. And for example, if the electron has come from the left input to and transmitted to the right with the photon absorption by the AC field, then n photon is observed with amplitude AN, and this amplitude is simply determined by the Fourier transform of the phase vector given by AC. And this phase vector is simply determined by this term, the red term, and it is the integration of the AC voltage signal from the initial time when the electron was deep in the contact to the final time when it escapes the contact. And this blue term is just a simple nth harmonic mode to obtain the Fourier transform. And here omega is the AC frequency. So the initial electron of energy E now gains energy, enhanced energy En, where the Hava omega is the energy quanta. And now when this electron encounters this resonance level, it transmits with the enhanced energy. So as a combined effect, the Fourier scattering amplitude for this event is determined by the photon absorption amplitude AN multiplied by the transmission amplitude in the static situation, but determined by the enhanced energy. And for example, if the electron has come from right reservoir and transmitted to the left reservoir, then the Fourier amplitude here is determined differently because of the chirality. So in this case, there is no photon absorption, and simply the amplitude is determined by the static transmission with the initial energy E. And remarkably, we find that in this case, power injection by AC voltage vanishes. So here is the power injection formula. And the red term here is mean energy change in photo-assisted scattering process from reservoir beta to alpha. So it's just the mean quantity averaging over all the other possibility further than I showed you before. And here the S square is the probability of each event, and N is the number of photons observed, and Hava omega is the energy quantum. And then this factor, blue factor, is the Fermi distribution from the input reservoir. And this factor, dE over high, is the injection rate on this energy window, delta E. So this determines the power injection. And due to the chirality, this mean energy change is always zero. For example, when the electron comes from the left input, it is zero because this energy change is determined by the DC average of the AC signal, which is zero for pure AC source, pure AC signal. And then also zero for the electron coming from the right input because there is no photon absorption at all. And I would like to emphasize that this conclusion is valid regardless of the form of the AC voltage signal. And for non-chiral conductors, the power injection is generally non-vanishing in contrast to this case. For example, when the driving is slow, for the adiabatic driving, we find that it satisfies the Joule's law. So the input power is proportional to the mean square of the AC signal. So for meaningful AC signal is always positive, which describes the dissipated power. And in these cases, we found that there was no significant efficiency enhancement due to the AC driving because of this power injection. So now I'll show you the numerical results, specific results. So here is the color plot of the efficiency divided by the Carnot efficiency. And x-axis is the average chemical potential, average between the left and the right reservoirs. And y-axis is the AC frequency. So you can see when we increase the AC frequency, generally the efficiency is enhanced. And for this, all the results, the best temperatures are chosen in the coherent regime, that every temperature is lower than the level Brody gamma, and chosen to be in the linear regime so that the temperature difference is smaller than the average temperature. And for each point, chemical potential difference is chosen to generate maximum power according to the linear response theory. And notably, if you focus at the mu equals 0 case, the driving realized genuine photoassisted thermoelectric engine. I will now tell you more specifically. So let's consider first the steady case along this line. And in this inset, the value of the chemical potential, the efficiency is plotted. So at this mu equals 0, which means the average chemical potential is aligned with the resonance level, there is no efficiency because it doesn't work as a heat engine. That is due to there is electron hole symmetry. So this is the transmission through the resonance level with respect to energy, and there is a symmetry around the chemical potential. This is I have to mention that we are using the Brett-Wigner resonance form for the transmission function as a model. And when we turn on the AC driving, then let's focus along this line. And in this graph, we can see at the same chemical potential, now there is a finite efficiency. And this is due to the electron hole asymmetry dynamically induced by levitons. And this inset shows the photon absorption probability distribution, where n is the number of photons. And there is asymmetry because leviton prefers photon absorption. And due to that, the total transmission, which is the summation of the transmission for all possible photoassisted processes, becomes asymmetric. And remarkably, the efficiency can even go beyond the Carnot limit, as indicated by these red regions with the number larger than 1. And we observe that this is always accompanied by negative value of the entropy production, but calculated assuming Clausius relation, this formula. And you can see when for the red region, there is a blue, which means the negative value of this entropy production. So it seems that the second law of thermodynamics is being violated, but this seeming violation can be resolved when we adopt the channel entropy as an entropy production. And this is already suggested by Bruch and Felix von Oppen in this paper for the non-Euclidean cases used by AC driving. So this quantity is determined by summation of the channel entropy flow for the ingoing distribution with the minus factor and the outgoing distribution, and is summed over all energies and all reservoirs. And we numerically observe that now this quantity is always positive without any contradiction like before. And now this deviation, the deviation of this quantity from the previous quantity, the Clausius relation, quantifies the non-Euclidean effect induced by AC fields. So we can see when we increase the AC frequency, this deviation grows. So as a final remark, I can give you the alternative interpretation that in our case, AC voltage behaved as a non-equivalent demon, which was suggested by Raphael Sanchez as treatment. So in our case, the demon, which is AC voltage, rearranges the electron energy distribution in a more uncertain way, thus violating the Clausius relation, but without injecting energy into the electron, the working substance, thus satisfying the demon condition. And one merit of our system is that our system does not need a fine tuning for satisfying the demon condition. you can recall that power injection by the AC field was 0 regardless of the AC signal. So this is the conclusion. So I showed you a class of the AC conductors, which shows the efficiency beyond the Carnot limits. And the seeming violation of second law is resolved when we adopt the entropy production based on the Shannon entropy. And here the chiral transport was crucial because there is no AC power injection. And we expect the experimental realization because this regime is approachable, realistic. So thank you very much. This is the end.
Thanks a lot. So we have plenty of time for questions. If anybody. So yes, Gwendal, please.
Yes, thanks a lot for the very nice talk. I have a question. You mentioned the effect of the frequency of these AC drives. What with the Leviton pulses, you can also tune the width of these pulses. Does it also has an effect on the efficiency?
Yes, exactly. So here I didn't show you, but in our preprint there is a result. So we can tune, for example, we can squeeze the width of the Levitons within the period to be much more narrow, right? And then non-Euclidean effect and the efficiency enhancement becomes stronger. That's because this quantity, the entropy, additional entropy due to the AC driving, this delta S, this quantity is determined by the fluctuation, the mean square of the AC voltage. So for the narrower Leviton pulses, there is a stronger, there is more energy uncertainty after being excited, right? So in the efficiency increased more.
Okay, thanks a lot.
Thank you.
Thanks. So other question, Gabriele, please.
Hello, hi. Can you hear me?
Yes.
Yes. So regarding the efficiency, I mean, it's always very strange to see efficiencies larger than Carnot. So I was wondering, is it possible to redefine a proper efficiency in such a way that, you know, Carnot efficiency is not violated? I mean, I understand that you resolve the problem of the entropy production, but if you want also an efficiency larger than Carnot is a violation of the second law. It's another way of violating the second law. So perhaps there must be a way in which you redefine the efficiency to take into account, for example, the entropy increase in the daemon, right? The information that the daemon is storing if it's acting on the system.
Yeah, thank you for the good question. Yeah, I think there is another way of defining the efficiency when you use information in the setups of the Maxwell lemma. But I'll first would like to mention that the efficiency defined in our work, just simple way of dividing the power output by the extracted heat, is always smaller than 1 because energy conservation is always satisfied. So in that sense, it's not that strange. But then it can be strange that the efficiency beyond the Carnot efficiency, right? Then we can define as a fundamental bound for the efficiency without relying on the Clausius relation. We can consider the second law, the positivity of the proper entropy production. I mean, this condition. Then we can define the upper bound for the efficiency limited by this condition. Then that value can be beyond the Carnot efficiency, but always the efficiency should be lower than this limit. But now we are not sure how to approach that bound. This is for the work that we should answer. So this is my answer. Thank you.
Thanks a lot. It's very interesting. Thank you.
Thank you.
Thanks. So there is one question by Rafael, please.
Yes. Hey, thank you for your talk. I'm a bit confused about when you say that the injected power is 0. because the average voltage by the AC field is the AC signal is zero. No? So this is true for sinusoidal pulses, but in Lorentzian pulses, is this also true?
Yes, I mean, here we define the AC voltage as a pure AC source. So always for a given time-dependent voltage, we can divide to the DC part and the AC part. And their AC part, I mean, when after time averaging being zero. So I'm defining the AC power to that part only. And as you know, in the thermoelectric engines, when you have a DC bias, you can always contribute to the power, but it's already considered in the thermoelectric power in this formalism. So,
okay.
Yes.
But you still have this Lorentzian pulse, no? Or...
Yes, in this case, I mean, we define the AC voltage for the Lorentzian pulse, but with the offset. With the offset, we satisfy that after being average, it becomes zero, but there is a fluctuation, right?
Mm-hmm.
And due to the fluctuation, there is always a non-recurring effect. There is an excitation of electron being more uncertain. And that makes the non-equilibrium effect, and that contributes to the efficiency enhancement over the Carnot.
Okay, thank you. I have to think about it. Thank you.
Thank you very much.
So thanks. Any further question? I would actually have one. So I'm wondering about the role that the levitons are actually playing, because what you say, if I understand correctly, is that what matters is the fact that they are strongly asymmetric, and that's what gives you the large contribution to thermal power. But now, can I think of something else than levitons that would have also very large asymmetry? Perhaps they wouldn't be minimally disturbing for the Fermi sea, but there might be even better types of driving for achieving the particular purpose you're looking for.
Yes, I think it's an important question. And actually, I forgot to mention that we also observed that for the sinusoidal simple signal, there is also efficiency enhancement over the Carnot efficiency. And what is special about the leviton is that this behavior. So, I mean, in the static case, it doesn't work as a heat engine, but if you apply the leviton, the Lorentzian pulses, then it starts to work as a heat engine. And that is due to the asymmetry induced by the Lorentzian signal. But in this case, if you apply the sinusoidal signal, then around this mu equals 0 point, there is no efficiency enhancement. But at this point, still we observe the efficiency enhancement. And I think it's also important question to furthermore exploring all the possible voltage profile to what is most efficient way to enhance the efficiency. Yeah, I think it's an important question.
Thanks. Are there any other questions? So just to make sure here, when you say the AC frequency, so of course your pulse is not sinusoidal, so it has higher Fourier components up to in principle arbitrarily large frequencies, right?
Yes.
So here, when you go from sinusoidal to levitons, you're changing the weights of the different higher harmonics.
Yeah.
And what you say is you only compared levitons, this particular shape, with just one tone, but in principle one could drive with many others, right?
Yes. Yes, that's right.
Because in particular, if you double the frequency, take a sinusoidal, but you double the frequency, I mean that sort of appears as a second harmonic to your signal, or I mean, can I?
Yes.
It seems to me that the higher you would, I mean, the stronger you would drive you would have in the high harmonics, the larger the effect you would observe.
Yeah. So basically, the non-recurrent effect depends on the fluctuation of the AC signal.
Mm-hmm.
So if you have larger fluctuation, then you induce stronger non-equilibrium effect, and the efficiency enhances more. So for that, yeah, I think it's better to have more harmonic components to get the higher fluctuation of the AC voltage.
Okay, thanks. One more question, Matteo.
Yeah, can you hear me?
Yes.
Yeah, so maybe it's a related question. Looking at your plots in this slide, it seems that by increasing the frequency, you also increase the efficiency, right?
Yes.
And so is there kind of a bound? Can you show that your efficiency defined in this way is bounded by something, or does it simply keep going, increasing with the frequency?
No. So yeah, I thank you for the good question. So if we further increasing, then there is more peculiar behavior. For example, yes, it usually goes out of the heat engine regime. I mean the heat, sometimes hot heat just dissipated through both reservoir, the cold reservoir and the hot reservoir, due to the too strong AC. And then we cannot define the efficiency in those cases. So yeah, I think for the more stronger regime, I think there is also interesting physics. But in the experimental situation, I think already like going near the non-adiabatic regime is already hard effort, I think. So we didn't explore much in that direction yet.
Okay, thanks.
Thank you.
Thanks. If there are no more questions, I would let's first thank. Sorry.
Oh, hello. Hi.
Hi. You have a question,
Yeah,
or?
I have a question, sir.
Okay, please.
Yeah, thank you for the talk, sir. Like, I'm an undergraduate student, so I had this question. Like, you say that it doesn't violate the second law of thermodynamics, but still the efficiency is more than what is predicted by Carnot engine. How is that possible? I don't know.
Sorry, can you speak up a little bit more? I didn't understand.
Yeah,
Well.
hello.
Yeah.
Yeah, so you demonstrate that efficiency is greater than what is usually predicted for Carnot engine.
Yes.
But it was, but you also verify the fact that you can redefine the entropy and preserve the second law of thermodynamics. So I don't understand, like if you preserve the second law of thermodynamics, how can efficiency still be, greater than what is predicted for Carnot engine?
Yes, that's because the Carnot efficiency is also requires the Clausius relation, that the entropy production is equal to this quantity. But in the strong non-equilibrium case, this can be broken, and that's the reason that in our case, efficiency can go beyond the Carnot, but still there is positive entropy production.
So this doesn't violate the second law of thermodynamics, right?
It doesn't break second law of thermodynamics. It only breaks Clausius relation.
Okay, thank you, sir.
Thank you.
Okay, so let's thank Sungguen again, and let